In the late 1950s, the largest steam locomotives ever built simply stopped. Within a few years, nearly the entire class was scrapped. No ceremony, no farewell tour. They were Union Pacific's big boys. 25 machines, each over 130 feet long, weighing more than 1 million pounds, purpose-built to haul wartime freight over the steepest grades in the American West. The absolute peak of steam power, discarded like surplus equipment. 8 escaped the cutting torch. But of those 8, only 1 runs under its own power today. What it took to bring that single locomotive back to life reveals why the other 7 almost certainly never will. The final revenue runs concluded quietly in July 1959. Without public fanfare, Union Pacific systematically moved these massive locomotives from active mountain service directly into cold storage lines at the Cheyenne yards. Their work was finished, and their sudden silence brought an immediate, unsentimental shift in railroad economics. Between 1960 and 1962, the railroad sold 17 of the retired units to commercial scrapyards. Workers dismantled the giant boilers and severed the heavy frames with cutting torches, turning proud mechanical achievements into heaps of raw steel. On the scrap lines, these mechanical giants were treated no differently than old boxcars or worn-out rails. The industry treated these engineering triumphs as surplus material to be recycled. Public crowds did not gather to watch them go, and commemorative excursions did not accompany their departure from the rails. This rapid, unceremonious retirement presents an unexpected historical problem. Usually, a machine of such cultural scale is granted a transition period to be appreciated by the public. Instead, these locomotives became obsolete before they could even be defined as historic. They vanished from the national landscape almost overnight, leaving behind a fundamental question. How does a symbol of national strength transform into simple scrap before anyone realizes what is being lost? The American Locomotive Company constructed 25 of these specialized machines in Schenectady, New York, between 1941 and 1944. Officially designated as the 4884 class, the completed locomotive and tender stretched over 132 feet in length, weighing more than 1 million pounds in working order. To the general public, its sheer mass suggested engineering excess. Yet every physical dimension was a calculated response to a specific mountain problem. The foundation of this design lay in its articulated frame. By splitting the driving wheels into 2 independent sets under a single boiler and hinging the chassis, the builders allowed this massive machine to bend through 20-degree mountain curves. Without this flexible joint, a rigid locomotive of this size would simply bind or split the rails. This giant was never intended as a general-purpose engine. Union Pacific contracted its construction for a highly specific assignment, dragging heavy freight over the Wasatch Range in Utah and the 1.14% grade of Sherman Hill in Wyoming. During the height of wartime traffic, the railroad needed to move 6,000-ton trains across these continental divides without the delays and labor of coupling auxiliary helper engines to the train. The immense mechanical specifications were direct results of this operational requirement. The massive boiler operated at 300 pounds per square inch of pressure, feeding steam to cylinders that produced over 6,000 horsepower. This pressure generated roughly 135,000 pounds of starting tractive effort, delivered to the rails through 16 68-inch driving wheels. The size of the grate, the capacity of the boiler, and the weight on the driving wheels were not designed for show. They were the exact physical measurements required to keep thousands of tons of wartime steel, coal, and military equipment moving up a mountain at 40 miles per hour. It was a single-purpose tool, built to conquer a specific bottleneck. Wartime mobilization in the early 1940s flooded the Union Pacific Main Line with historic levels of military freight. Steel, coal, vehicles, and ammunition had to move without interruption from Midwestern factories to Pacific ports. This massive surge in traffic ran directly into a physical bottleneck in western Wyoming and Utah. Here, the Continental Divide presented an unyielding obstacle course, defined by the grueling climbs of Sherman Hill and the sustained grades of the Wasatch Range. These were not short, steep ridges that a heavy train could conquer with a brief burst of momentum. Instead, they were long, exhausting ascents stretching over dozens of miles, requiring steady, maximum power. On Sherman Hill, trains faced a steady 1.14% climb for over 30 miles. In the Wasatch Range, the grades climbed even higher, forcing locomotives to work at their absolute limits for hours, fighting both gravity and the thin mountain air. Before this crisis, the standard solution to these mountain obstacles was the helper engine. When a heavy freight train reached the base of the grade, yard crews would couple extra locomotives to the train to help push and pull the cargo over the summit. But this practice created a massive operational bottleneck. Helper engines consumed extra crews, pulling valuable workers away from other essential runs. They burned through vast quantities of coal and water, requiring frequent stops that delayed the entire line. Worse, once a helper engine reached the top of the mountain, it had to be uncoupled and run back down the hill. These return movements clogged the single-track main line, reducing the overall capacity of the railroad at a time when every hour mattered. The human cost fell squarely on the Mountain Division crews. Engineers, firemen, and brakemen operated in a state of constant exhaustion, managing the complex logistics of coupling, uncoupling, and watering multiple steam engines on exposed mountain passes in sub-zero winter temperatures. The railroad was operating a fragile system of short-distance helper runs on a route that needed to function as a high-speed transcontinental corridor. This mountain-grade crisis required a different approach. The solution was not to build a versatile, general-purpose locomotive that could run anywhere on the system, but to design a specialized tool tailored strictly to the geography of this single route. The value of this new design lay in its ability to streamline operations, replacing multiple helper crews and engines with a single machine that could keep thousands of tons moving over the Continental Divide without stopping. The American Locomotive Company delivered exactly 25 of these massive machines, and then production stopped forever. No successor class was designed, and no subsequent family of locomotives evolved from their blueprints. The entire lineage ended exactly where it peaked, with no future descendants. This abrupt halt reveals a stark mechanical irony. The ultimate expression of American steam power arrived at the precise historical moment its operational future began to contract. By solving the Continental Divide bottleneck through sheer physical scale and specialized engineering, the railroad pushed reciprocating steam technology to its absolute thermodynamic limit. There was simply no physical room left to grow and no economic incentive to try. These 25 locomotives represented the final summit of an old era rather than the start of a new one. They were highly specialized, monumentally complex answers to a geographical crisis, completed just as the entire steam paradigm faced systemic obsolescence. When the last unit, number 4024, rolled out of the Schenectady shops in September 1944, the industry was already transitioning toward a different, more efficient source of motive power. The greatest steam engine ever constructed was an engineering triumph, but it was also a glorious, irreversible dead end. The diesel-electric locomotive replaced the big boy despite having less single-unit horsepower. A single 4884 could still haul thousands of tons up a mountain grade. Instead of raw muscle, the diesel won by fundamentally restructuring railroad economics. The shift began with how power was generated and controlled. Diesel electrics used internal combustion engines to turn generators, sending electricity to traction motors on the axles. More importantly, multiple diesel units could be linked together and controlled by a single engineer using multiple unit cable connections. Under steam operation, each additional locomotive required its own highly skilled crew. With diesels, a railroad could chain 3 or 4 units together to match or exceed the big boys' tractive effort while using only one engineer. The second seat in the cab, the fireman, who was required to manage a steam boiler's volatile coal and water levels, disappeared from normal operations. This structural shift in labor cut crew hour expenses by 70%. The physical demands of steam operation also carried severe logistical penalties. To travel 100 miles, a big boy consumed 28 tons of coal and 24,000 gallons of water. This forced trains to halt every few dozen miles for 30 to 45 minutes just to refill the tender. These frequent stops clogged the busy single-track main line and wore down overall operating efficiency. A diesel locomotive, by comparison, required no water for propulsion and could refuel in less than 5 minutes, keeping heavy freight moving over the mountains without interruption. Behind the scenes, the maintenance burden broke the back of steam technology. Steam locomotives required constant attention from specialized roundhouses, heavy coaling towers, and water treatment systems. Their boilers required regular washouts, and their complex moving parts demanded hours of manual lubrication after every run. This kept steam locomotives out of service for long periods, resulting in an operational availability rate of about 65%. Diesels offered a modular alternative. Components could be swapped out quickly, keeping locomotives on the track and raising availability to 95%. This modular design also allowed railroads to dismantle their expensive water tanks, coal chutes, and massive turntable facilities, drastically simplifying their physical footprint. Union Pacific operating reports from the mid-1950s captured the finality of this transition in raw numbers. The fuel cost per ton-mile for steam stood at 45 cents, while diesel accomplished the same task for 12 cents. The economics collapsed underneath a machine that was still fully capable of doing its physical job. Railroad management, acting as a modern business institution, chose systematic dieselization because the steam locomotive had become an expensive operational liability. The transition from steam to diesel culminated in a quiet, procedural exit. On July 21, 1959, the final revenue runs of the class concluded over the Laramie-Cheyenne line, with engines like 4015 hauling their last freight tonnage before rolling onto the storage tracks. There was no grand public ceremony, no national farewell excursions, and no civic fanfare to mark the day. The railroad parked these million-pound machines in cold storage lines at the Cheyenne yards, treating them strictly as retired industrial assets that had reached the end of their operational utility. Official retirement followed in the early 1960s, ending with the formal withdrawal of the final 5 units from the active roster in July 1962. During this period, the scrapyard became the primary destination for the class. Union Pacific systematically sold 17 of the 25 locomotives to commercial steel recyclers to recover their material value. In July 1961, for example, the railroad dispatched locomotive 4001 to the St. Louis Steel Company, where demolition crews used oxygen-acetylene torches to dismantle the boiler and cut the heavy articulated frame into heaps of raw scrap. These mechanical giants were treated no differently than obsolete boxcars or worn-out rails. They vanished from the national rail network as retired equipment before the general public or the industry fully recognized them as historic heritage. Yet, while 17 units went directly to the cutting torch, 8 managed to avoid destruction. Their survival under these rapid, unceremonious conditions raises an unresolved historical question. How did a small group of these obsolete giants manage to escape the scrap line when the rest of their class was so quickly turned to dust? Against the odds of the mid-century scrap lines, 8 of these massive locomotives survived. Today, they form a remarkably intact record of a vanished era, scattered across the United States in the custody of diverse caretakers. This roster of survivors comprises numbers 4004, 4005, 4006, 4012, 4014, 4017, 4018, and 4023. Each of these remaining units represents a distinct preservation victory, safeguarded by a patchwork of public and private institutions. In Cheyenne, Wyoming, the city holds the title to 4004, maintaining it as a public monument. Number 4005 rests safely indoors at the Forney Museum of Transportation in Denver, Colorado. In St. Louis, Missouri, the National Museum of Transportation preserves 4006. Further east, 4012 resides at the Steamtown National Historic Site in Scranton, Pennsylvania, under the care of the National Park Service. Meanwhile, the Museum of the American Railroad in Frisco, Texas, holds custody of both 4017 and 4018. In Omaha, Nebraska, 4023 stands in Kennefic Park, while 4014 remains under corporate custody in Cheyenne. On the surface, this high survival rate looks like an overwhelming triumph for industrial preservation. These 8 machines escaped the cutting torches that claimed the rest of their class. They exist today because local municipalities, nonprofit museums, and dedicated heritage groups stepped forward to claim them. Yet physical survival is merely the first step. While these 8 steel giants physically exist in the 21st century, their placement in parks, roundhouses, and museums reveals a different reality. Keeping a locomotive from being melted down does not guarantee its future, nor does it make these machines equal. Beneath the surface of this apparent success lies a silent, stark division. Under their current custodial arrangements, 7 of these surviving locomotives will never move again under their own power. These 7 machines are static displays. This status represents a successful and highly valuable form of stewardship. Local cities, historical societies, and nonprofit museums have successfully protected these massive objects for decades. They repainted the boilers, oiled the bearings, and built protective shelters, keeping the physical history of the steam era accessible to the public. However, a vast mechanical gulf separates a cosmetic exhibit from a locomotive authorized for mainline service. A static display requires cosmetic care, rust prevention, and basic structural safety to stand in a public park or museum hall. An operational locomotive must function as a living utility. It must meet rigid Federal Railroad Administration safety standards, maintain a highly trained crew, pass intensive mechanical inspections, and satisfy the operational demands of a modern mainline railroad. Today, only one big boy, number 4014, meets these challenges and runs under its own power. For the other 7, the fireboxes remain cold, the boilers dry, and the heavy rods silent. They are preserved artifacts, while their sibling travels the country as an active machine. This operational divide exists because of practical realities rather than luck or neglect. Returning a million-pound steam giant to the rails is an extraordinary undertaking that goes far past basic preservation. It requires resources, infrastructure, and institutional support that few organizations on Earth can provide. To understand why only one of these giants still breathes, 3 fundamental questions must be answered. First, what does it actually take to rebuild a high-pressure boiler to modern safety standards? Second, how does any organization secure the millions of dollars required for such a project? And third, where can a locomotive of this scale actually run in a modern rail system that was not built to support it? A steam locomotive boiler is, at its core, a highly volatile pressure vessel. Operating at 300 pounds per square inch, a big boy's boiler holds immense destructive energy. If the steel shell fails, superheated water instantly flashes into steam, creating a catastrophic explosion. This physical reality is why a cosmetic restoration in a public park is functionally light years away from an operating machine. Federal safety authorities draw a strict line through the Federal Railroad Administration's Part 230 regulations. Under these federal rules, any steam locomotive operating on the main line must pass a rigorous 1,472 service day inspection. a process that must occur at least once every 15 years. This is not a bureaucratic exercise. It is an exhaustive mechanical autopsy. To satisfy federal inspectors, boiler specialists must strip the locomotive down to its bare metal. Crews remove the sheet metal outer jacket and the thick layers of insulation lagging that cover the boiler. On the inside, workers extract all the superheater elements and thousands of heavy boiler tubes, leaving a hollow steel cylinder. Only then can the diagnostic work begin. Inspectors cannot judge a boiler by its external appearance. Steel that looks smooth and freshly painted on the outside can be dangerously thin on the inside, worn down by decades of oxygen and mineral corrosion. Specialists map the entire structure using non-destructive examination, relying on ultrasonic testing to send high-frequency sound waves through the metal. This process measures the thickness of the boiler plates down to a fraction of an inch, searching for hidden thinning in the firebox sheets, wrapper sheets, and the mud ring where sediment historically settled. Bracing the inner firebox against the outer boiler shell are thousands of individual steel stay bolts. Every stay bolt must be physically evaluated. Inspectors hammer test each bolt, listening closely to the pitch of the ring to detect internal fractures that the eye cannot see. The ultimate test of structural integrity is the hydrostatic test. Workers fill the stripped boiler with water warmed above 70 degrees Fahrenheit and pump it up to 25% above its maximum working pressure, pushing the gauge to 375 pounds per square inch. Under this load, inspectors examine every seam, rivet, and stay bolt for the slightest sign of weeping or metal deflection. The age of these machines introduces another obstacle. Most static survivors spent decades running on different divisions, exposing their metal to varied water chemistry that caused localized pitting. Many received undocumented repairs in regional roundhouses during the high-pressure years of the war, leaving behind non-standard welds that fail modern safety standards. For municipal parks and volunteer-run museums, this mechanical reality is a complete barrier. They lack the heavy-lift cranes, the specialized diagnostic tools, and the certified boilermakers required to perform this highly regulated work. Without these resources, the boiler remains a cold, unpressurized shell. The 7 static locomotives that remain on display across the country represent extraordinary victories of local preservation. Municipalities, regional museums, and nonprofit groups stepped forward when these engines had no commercial value, saving them from the cutting torch. Today, these organizations manage the daily care of these massive artifacts. They clean the boilers, apply fresh coats of paint, and build protective canopies to shield the steel from snow and rain. For a local museum or historical society, this visual upkeep is a major achievement, often funded by small donations, museum ticket sales, and volunteer labor. But maintaining a static monument is fundamentally different from operating a live locomotive. The financial gap between cosmetic display and mainline operation is massive. When Union Pacific restored number 4014, the project required an investment estimated between $12 and $15 million over several years. That scale of funding is entirely out of reach for a typical municipal park or local historical society. A volunteer-run museum might successfully raise $50,000 to paint a boiler, but raising millions of dollars for an industrial overhaul is a different challenge altogether. The financial barrier does not end once the locomotive is rebuilt. Operating a million-pound machine means accepting a continuous cycle of expensive obligations. Every mile on the main line generates costs for fuel, track access, and highly trained operational crews. Custom parts must be forged in professional machine shops because replacement components for a 1940s steam engine have not existed for over half a century. On top of that, mainline operations require massive liability insurance policies, regular regulatory inspections, and constant mechanical servicing. While public affection for these historic machines is immense, admiration cannot fund a heavy rail program. Without the backing of a Class I railroad, The financial and operational demands of a functional big boy are simply impossible to sustain. The 7 static survivors remain safe because their caretakers protect them, but they remain silent because only an active railroad company has the capital to make them breathe. Once a locomotive rolls out of the restoration shop, it meets an unyielding gatekeeper, the modern rail network itself. A fully loaded big boy and its tender weigh nearly 1.2 million pounds, transferring an axle load of roughly 73 tons to the track structure. To support this massive weight, the route must feature heavy mainline rails, weighing at least 115 pounds per yard, laid over deeply ballasted ties, and backed by steel and concrete bridges rated for a minimum of 400 tons. Many regional short lines, scenic railways, and preservation tracks cannot support these extreme axle loads, instantly cutting off most potential routes. Even on high-capacity rails, physical clearances present a constant barrier. The big boy stands 16 feet, 6 inches tall, and 10 feet, 8 inches wide, with a long, articulated frame that swings wide on curves. This massive clearance envelope restricts where the locomotive can travel. Before the wheels can turn, engineers must perform a series-by-series review of the planned itinerary, checking for low overhead highway bridges, tight rock cuts, and narrow passenger platforms that would collide with the locomotive's boiler or tender. Servicing is another daunting logistical challenge. Unlike modern diesel locomotives that run for days without attention, a big boy's tender requires 24,000 gallons of water and 5,000 gallons of fuel. Operating on modern tracks means pre-positioning water trucks and fuel pumps at precise intervals along the main line, turning brief servicing stops into complex local operations. Once the train reaches its destination, it cannot simply reverse. Turning a locomotive of this length requires a massive Y track or a specialized 125-foot turntable, facilities that have vanished from almost all modern rail yards. Beyond these physical demands, the administrative hurdles are immense. Operating on tracks owned by other freight carriers requires formal host railroad agreements, specialized dispatching to avoid clogging active cargo lanes, and liability insurance policies of at least $5 million. The people in the cab must be highly specialized, federally certified crews who understand the mechanical temperaments of 20th century steam. When these requirements are added together, the heavy bridges, the strict clearances, the specialized fueling, the dispatching coordination, the $5 million insurance, and the certified crews, the true barrier to operation becomes clear. Only one surviving owner in the entire country already owns and controls this entire complex system, leaving all other preservation groups locked out of the modern main line. Union Pacific remains the only corporate entity with the track, the workshops, and the financial motivation to maintain an operating 4884. While the other 7 surviving engines belong to municipal parks, regional museums, and nonprofit preservation groups, number 4014 belongs to an active Class 1 railroad. This corporate connection provides resources that do not exist anywhere else in the preservation community. The centerpiece of this capability is the Cheyenne Heritage Steam Shop in Wyoming. This facility is a fully equipped industrial plant, staffed by professional machinists, heavy-duty boiler makers, mechanical engineers, and federal inspectors. Instead of relying on weekend volunteers and public donation drives, the Cheyenne shop operates with full-time railroad employees who possess specialized heavy equipment, industrial cranes, and custom machining tools. The restoration of a million-pound steam engine requires a continuous commitment of professional labor and corporate capital. This industrial alignment drove the modern history of number 4014. In July 2013, Union Pacific reacquired the locomotive from the Southern California chapter of the Railway and Locomotive Historical Society in Pomona. The engine had spent 5 decades in the dry West Coast climate, which kept structural corrosion to a minimum. After completing a nominal purchase, the railroad organized a complex overland transport, moving the massive machine to the rail connection before towing it back to the Cheyenne shops to begin the multi-year project. The work was executed as a coordinated industrial overhaul rather than a simple volunteer restoration. Workers stripped the locomotive down to its bare frame, allowing engineers to map the entire boiler structure. Technicians logged thousands of restoration items, replacing thousands of stay bolts and installing new boiler tubes to meet federal safety standards. While project manager Ed Dickens served as the public face of the operation, the actual execution depended on the daily labor of the entire shop workforce, working together to rebuild the giant machine piece by piece. During this reconstruction, the shop team converted the locomotive from coal to oil firing. They replaced the original coal grates with a dual oil burner system and modified the tender to carry fuel oil. This mechanical shift eliminated the labor-intensive coaling stops and reduced trackside fire hazards along modern main lines, making the engine far more practical to run on a modern rail network. After 5 years of reconstruction, number 4014 returned to steam in May 2019. The timing coincided with the Golden Spike sesquicentennial, marking the 150th anniversary of the Transcontinental Railroad's completion. When the locomotive rolled out of the Cheyenne shop under its own power, a preserved museum artifact became a living mainline locomotive once again. The successful operation of this machine is not a matter of luck or superior preservation. The other 7 survivors are valuable historical successes, representing decades of municipal and volunteer care that saved these giants from the scrapyard. Yet, number 4014 runs because of direct corporate ownership, professional industrial facilities, and a specific business purpose. Union Pacific continues to operate the engine because it serves as a powerful symbol of corporate identity and historical heritage. Yet this arrangement depends on a specific set of corporate priorities: active shop space and an open main line. How long these internal railroad conditions will last remains an open question, leaving the future of the world's largest operating steam locomotive tied directly to the shifting priorities of the corporation that brought it back to life. Locomotive 4014 does not run today because of simple luck. It was not preserved in any better state than its 7 silent siblings. The other survivors on display across the country represent great preservation victories. They stand as well-maintained records of a past era, kept safe by the cities, local museums, and volunteers who protected them from the scrap lines when steam power died. But a museum can only preserve a machine. It cannot operate one. Rebuilding and running a million-pound steam engine on a modern main line requires an entirely different level of physical and financial resources. It demands a complete industrial network that only a major transport corporation can provide. The direct answer to why only one big boy operates lies in this corporate network. Locomotive 4014 is the product of an industrial system controlled by Union Pacific. No other preservation group possesses the necessary combination of Class 1 railroad ownership, massive corporate capital, a fully equipped heavy repair shop, federally certified crews, and compatible mainline track. Most of all, the railroad has a clear business purpose to keep the engine running as an active symbol of its heritage. Without any single piece of this corporate network, the giant would instantly fall silent. As 4014 travels the country, its movements expose a fragile reality. This massive machine runs only because its owners choose to support it, leaving its operational future bound to the shifting priorities of a modern company. How long those specific corporate conditions will last remains a question with no answer. The 7 static survivors are not failures of preservation. While they do not simmer with live steam, their quiet presence across the nation is the very reason the big boy class can still be seen, studied, and remembered today. Static preservation and active operation simply serve different historical purposes. A display in a museum or park keeps the physical record secure, stable, and accessible to generations who might never see a mainline excursion. These silent giants protect the physical memory of the class, offering a permanent connection to the past that does not depend on corporate balance sheets. Together, the 7 static displays and the 1 active runner form the complete record of the 4884. Meanwhile, the life of number 4014 remains alive, but incredibly fragile. Its continued operation is not guaranteed. It rests entirely on a delicate alignment of corporate funding, federal safety regulations, compatible rail infrastructure, qualified crew members, custom fabricated parts, and an ongoing institutional commitment from Union Pacific. If any single piece of this complex network shifts, the great locomotive will return to the silence of its siblings. The ultimate question of the big boy story is not just why one locomotive runs today, but how long the fragile conditions that keep it running will last. Today, 7 static giants safely guard the past, while number 4014 carries it into the present. Yet this living legend depends entirely on a fragile corporate ecosystem. The ultimate question is not how long these machines can physically endure, but how long a modern corporation will choose to support them. Until those priorities shift, we must appreciate the thunder while it lasts. What do you think the future holds for number 4014? Share your thoughts below.